going to give a talk. My talk is going to be that is the subject. Now, people will be very surprised that I have said Aryabhata needs a reassessment. We all know he's been assessed enough. Everybody has looked at him. Every Indian, every person interested in the history of mathematics in India has put Aryabhata on a pedestal. He has been idolized, worshipped, criticized, especially when soon after he did his work. So, nevertheless, there are many places in the text which, when you go back and look at them with what we know today, with a sharper eye, can actually stand a certain degree of reassessment. About Madhava, my feelings are much stronger in the sense because he's 25 years ago, no one had heard of Madhava's name. Except a few professionals. So, in his case, I should remove the re. It is actually an assessment of Madhava's work. I have been trying to do this for the last few years, and I find that it hasn't had a great deal of. It hasn't caused any revision in our rather poor understanding of Madhava's work. There have also been many obscurities in their personal histories, both in Aryabhata's case and in Madhava's case, and clarifying those issues, in my view, contribute not only to understanding what they were, not only what they were in their bodily lives, but their disembodied spirits. Their mathematics itself is to some extent better understood if you understand their personal histories. So that's the reason why I'm giving this talk. Now, it's bound to be somewhat polemical, naturally, because I should say not just polemical, polemical. There are issues which are connected with the influences on their work, the sources of inspiration, the legacies they left behind, what people made of their teachings later, sometimes poorly understood, often correctly understood, but sometimes very badly missed. Now, of course, Aryabhata is a mathematical astronomer. So, astronomy, he's made several seminal contributions, and the basic source of his inspiration is very definitely Hellenic astronomy, mathematical astronomy. Whether that influence came at the time from the person who was the most widely known of the Greek astronomers, that is Claudius Ptolemy, or from earlier Greek mathematicians and especially geometers, is an issue about which I find that there is not a great deal of unanimity. I hope to make a case that it actually is Ptolemy whose work strongly influenced. I don't do it in very great detail, but that's the case. Ptolemy is very clear. If you go through the details, it's very clear. It's Ptolemy who's influential. The idea came from Greece that you can actually make a geometrical model, use the geometry to predict the future behavior of heavenly bodies. That, of course, led to the idea that, if I can predict the trajectory of the universe, the visible universe, starting with information at one instant of time, then surely I should be able to do it for human lives, which are, a tiny part of the universe. If I know the epoch, the correct epoch is the time of their birth, and it must be put in the context of the local time. Therefore, it depends on where you are born, and that is astrology. And Ptolemy was, of course, as famous as an astrologer, probably more famous as an astrologer. And horological astrology came to India at about the same time. If you read Varahamihira, for example, who wrote Panchasiddhantika, which is an astronomical text, also wrote the Brihat Samhita, which contains a fair amount of astrology. So astrology came to India in this way. We didn't have this kind of astrology from before, from earlier. It came from the Greeks. Now, among the Aryabhata's great insights is the visible universe is a periodic something whose evolution in time is periodic, even though time itself is anadyanta. It's no beginning, no end. That, of course, caused a great deal of opposition at that time. Then other things, well-known thing. Now, the most important thing, of course, is the notion of the spinning earth. It is not the fixed stars which rise in the east and set in the west. It is the earth itself which is turning on an axis from the west to the east. Now, as is well known, this met a great deal of opposition, and in the text itself, the verse immediately following the famous analogy in which Aryabhata talks about relative motion being the only observable motion that we can have. That is to say, the famous verse about the boat going down the river and seeing things, fixed things moving backwards. The following verse, which talks about a thing called the pravaha wind, whatever it is, pushing the fixed stars from the west to the east, counters this. Now, this, I call it a counterfeit verse. It's a case of censorship because the verse itself is completely inconsistent. No remotely competent astronomer will say that the planets, the fixed stars, as well as the planets, will be pushed due west, samapaschima, by any wind. We know that the motion of the planets is very irregular. So no competent astronomer would have done it. So this is something which was imposed on the text from outside. What's interesting is that the book itself is known as Aryashtashata, 108 verses, if you keep the Gitika out. So that means that it still has 108 verses. So this verse is actually, it has replaced something else which was there. What that something else was, we don't know. It's my view that there is another counterfeit verse in Aryabhatiya, which is the last verse, or the last but one verse, in which he talks about his following the Swayambhava system of planetary motion. I'll come to that in a minute. For the time being, just keep in mind that I think it's also. Then, of course, the text is full of correct Aryabhatan astronomy, which contradicts this verse 10 of the Gola Pada. In the beginning itself, it says all the planets have a certain period, except, and it says in connection with the earth, he uses the word prak. That is, it is moving towards the east. So there are many, many indications that all of this is fake. These are days in which fake news, fake things are very popular. So the mathematics itself was, he got from India. He didn't take it from the Greeks. Astronomical idea came from the Greeks. Mathematics itself either can be traced back to the Shulva Sutra, or even when it can be traced back to the Shulva Sutra, he has transformed it in very original and very creative ways. So the mathematics is a mixture of what was already known and his own inventions. And trigonometry is one of his inventions. Now, trigonometry is not just geometry with numbers thrown in. Euclid has very few numbers. The geometric parts has very few numbers. In fact, first 5 books I read through once very carefully, and I found exactly one number, or maybe 2 numbers. Both are 2. And one of them says that the area of a parallelogram is twice the area of a triangle with the same base and the same altitude. That's the extent of the numerical geometry in Euclid. There's very little of it. It's very difficult to understand why numbers were kept away from geometry. Indian geometry from the beginning had numbers, from the beginning. Along with the statement of the theorem of the diagonal, which is more commonly known as the Pythagorean theorem, there is a list of Pythagorean triples, that is triples of integers, positive integers, which actually satisfy the identity z square is equal to x square plus y square. So numbers were part of Indian geometry from the very beginning. So trigonometry wasn't a particularly difficult thing to do. What is trigonometry? What it does is you want to measure, you want a relationship between arcs and chords. That's the origin of trigonometry. Trigonometry is really geometry of the circle. So what you do is you take an arc AB, you make it twice its length, AC, ABC, and you take the chord and take half of it. Okay. Now the association, the correspondence is between the arc AB and the triangle, the right triangle AOP. That's a 1-1 correspondence. So once you know the arc, you know everything. OA in my notation, in my conventions, OA is 1. I'm working with the unit circle. So AP is the sine and OP is the cosine. And the content of the theorem of the diagonal is the statement sine square theta plus cosine square theta is 1 for any angle theta. That's what it is. Now, the basic geometric fact behind this is what I call Indian orthogonality. I call it the Indian orthogonality. I don't have the time to do it in any detail, but the basic theorem is that a diameter which bisects a chord is perpendicular to the chord. In particular, if I have two circles intersecting, the line of centers cuts the common chord perpendicularly. Now, this is a result which goes back to the Indus Valley civilization. There's been a fair amount of work, not fair amount, a certain amount of work in the last few years on what we can learn about the geometrical knowledge of the Indus Valley people from their decorative patterns and from the fact that they had perpendicularly intersecting, cardinally oriented streets, a fair number of them. There's been a lot of talk about how they determined these things. There's a lot of writing on it. And it's pretty clear now that both these facts fit very well if we accept two things. One is this theorem, Indian orthogonality, especially of equal circles. Equal circles intersecting always produces wonderful patterns. The streetscapes are very easy to produce this way. But much more important are the decorative patterns on their artifacts, in particular the jars. Unfortunately, I don't have pictures of them. I have them somewhere or the other. And if you look at them, and this is the work primarily of a physicist in IMSC, Institute of Mathematical Sciences, Sitabra, who has analyzed these decorative patterns from the point of view of a crystallographer. What is the unit cell? He identified the unit cell. The unit cell is very, very closely related to this construction. And my feeling is that Aryabhata thought of this half the chord of twice the arc, the definition of the fundamental definition in trigonometry, because the same Bauthayana Shilpa Sutra has a procedure for determining the east-west and the north-south in one this thing. Of course, there are no reasons are given, but if you follow the pattern, this is what happens. This is what I don't like these things. Why they won't make a pointer in which the up-down buttons are clearly separated from the pointer button, I'll never understand. There you are. Yeah. So that's this diagram. You can see there's the same diagram effectively. And this is the shadow method of determining the true east. And this almost certainly is the way in which the Indus Valley people determined their north, south, east, west orientations. Okay. The reason why this was a stroke of genius, this going to twice the arc and then taking the chord and taking half of that chord is a stroke of genius, because this length captures fully the symmetries of the circle, this half chord. Among other things, it captures the symmetries of the thing. For example, sine pi minus theta is sine theta is a fact used by Aryabhata because his table stops at pi by 2. Actually, you can stop at pi by 4, but he stops at pi by 2. Why is that? That's because the others can be these supplementary angles. Supplementary angles can be determined that way, because if I take this arc and I take the supplementary arc and I double each of them, then of course the chord is common. AC is the common chord. This and the other one which goes the other way. This and this. And you know this without taking square roots, because the what I call Greek orthogonality, which is the one Ptolemy used for his chord table. It's not a half chord table; it's a chord table. Is the what I call Greek orthogonality, which is what? Which is the fact that this. Where is it? Why is it not coming? Anybody see the red spot? Ah, there. Which is the statement that this chord and its supplementary chord, this chord and its supplementary chord, which is this angle is a right angle. That is a diameter subtends right angle at the circumference. So if you want to go from one to the other, you take square roots, because you're going to use Pythagoras' theorem. Sine square plus cos square equal to 1. So Ptolemy is doubled his work because he didn't have the symmetry. And symmetry is very natural with a half chord. It's not very natural with a full chord. So that's the reason why I make this distinction. Now, why is this half chord idea so important? Because every arc can be related to its half chord, and every proposition on any linear figure connected with the circle, in particular polygons inscribed in a circle, or polygons which circumscribe a circle, can be given a trigonometric formulation, because they are chords of arcs. And when you do that, you can use the identities that come from the symmetries to prove anything. So in particular, all circle theorems have a trigonometric formulation and a trigonometric proof. So, this makes it very easy for us today now to take standard theorems, like for example Ptolemy's theorem in geometry, and turn it into a statement about trigonometry, a trigonometric statement. Of course, that doesn't mean that the Greeks knew trigonometry, because if they did, they wouldn't go through the extra work. Now, this distinction is not something that is newly arrived at in the last 10 years. John Playfair's famous article on the trigonometry of the Hindus, what is it called? Trigonometrical Tables of the Brahmins, published at the end of the 18th century. That's almost 2.5 centuries now. Makes this point very clearly. And he said why Ptolemy needed Ptolemy's theorem. It wasn't in Euclid. He had to find one because he wanted to find the chords. Then he said how the Hindus, how the Brahmins, not the Hindus, how the Brahmins solve the same problem in a much more simple. So trigonometry is, for me, is a subject founded by Aryabhata. That is not a universally popular thing. This is a technical thing which I will describe in a few words. Don't pay too much attention to it. Aryabhata's method of determining the sign table, determining the values of the signs or the sign differences, is very deep in origin, very easy in implementation. What you do is you divide the circle into 96 equal parts. Okay, that step size is what I call epsilon. There. You define the sign as you define Sm as the sign of an m-fold multiple of epsilon. You define the differences here. And then there is a formula which is very, very easy to derive, no hard work at all, which tells you what these differences of sines and cosines are. It is the same what we know today, that is sine m plus epsilon minus sine m minus epsilon is sine epsilon. Use the addition formula, subtract it, you get sine m epsilon and a cosine epsilon. That's what you'll get, with a factor of 2, I think, somewhere or the other. Then, in terms of step sizes, this is what it is. Now, when you see this kind of thing, you have sine. Oh, I made a mistake. This is a cosine. I beg your pardon. So when you see you can do a similar thing for the cosine, and you combine them, you get this equation. No, no, this is correct. I beg your pardon. This is correct. This is the second difference, you know. There is a delta. I take the second difference, I get the sign on the right. This is the discrete equivalent of the harmonic equation. Delta square sign is minus sign. That's what it is. So you have this equation to solve. How does he do it? He uses the fact that each difference is the sum of other differences. That is, he uses the fundamental theorem of calculus in its discrete form, which says what? Which says that the sum of the whole is the sum of the parts. That's what it says. So when you do that, you get a certain equation, and that is the equation here. This is exact. This equation in red is exact. What he then does is to make two approximations. One is that the sign of the first step, epsilon, is replaced by epsilon because it is a small enough angle. The second thing is that if you compute delta S2 minus delta S1, turns out to be minus 1 minute. He measured everything in minutes of arc. So that factor, this factor will become 1. So it will disappear from the equation. Caused a lot of confusion. People used to wonder where this, how he can drop this term. This is the reason why he can drop this term. This was made clear by Nilakantha in his beautiful commentary on this formula in the Aryabhatiya Bhashya. Now, what's important is that when you want to do trigonometry, you're comparing arcs and chords, you're comparing arcs with linear, straight lines. And you must measure everything in the same units, otherwise you will get funny results. You'll have to constantly use conversion factors. So avoid that. Aryabhata, today we use the radian angle, the radian measure of the angle to do this, because then it becomes dimensionless and everything goes through very well. It's not just that formulas will have extra factors, but it's a natural thing to do. You must measure, you can't compare apples and oranges. So you must make everything into apples. Now Aryabhata uses this, and then angular units for both. Circumference is measured in degrees. That comes from Greece, 360 degrees. That's 21,600 minutes, and you compute the radius corresponding to this in minutes of arc, you get this famous number, 3,438 minutes of arc. For the value of pi, which is 3.1416, which is also due to Aryabhata, that particular number. Now, the half chord needs a value of pi. Otherwise, because that's the ratio between the diameter and the circumference. So every person who has done this kind of thing, I mean, Aryabhata, for example, Ganitha 9 or Ganitha 8, I've forgotten which, it comes before the Aryabhata rule, which is Ganitha 12. So it has to come before. So that's why this value is given. And the same thing happens in Yukti Bhasha. Chapter 6 precedes chapter 7. Now, the number 3438 was the center of a certain amount of activity among mathematical historical circles at a certain time, and not so long ago. And when I first read about this, and I was extremely puzzled, and said the claim was that 3438 occurs in the table of Hipparchus. Hipparchus' conjectured table of chords or half chords, we don't know what. So much was said, and then it said, 3438 minutes occurs in Hipparchus' table. Therefore, Aryabhata's trigonometry came from Hipparchus. Of course, first of all, if Hipparchus really had 3438, he would have had to do two things. One is he must measure the radius in minutes of arc, for which there is no evidence whatsoever, zero. In particular, especially Ptolemy, who made a chord table, if he had known about the use of the same units for the circumference and the diameter, he would have himself used the same units. He hasn't. And that's one of the reasons why Ptolemy's table is hard work. So Ptolemy didn't know this idea. Ptolemy knew Hipparchus's work very well, so I would imagine that Hipparchus did not have the idea of measuring lengths in minutes of arc. Then, having got this idea, he must then have a value of pi, because r is 2 pi divided by 21,600 divided by 2 pi. So, what is the value that pi had in Greece of, the first time I've had a dog listening to me. Seminar. Yeah? IIT. Yeah, very good. So, I went back and looked, what value did they have? Archimedes, before him, had a value of, had this inequality. If you look at this inequality, this is what you get for R. It lies between 3425 and 3445. Ptolemy, who came substantially later than him, had this value, rational number approximation. This one. That gives 3437, not 3438. There is a difference between 7 and 8. These are not experimental numbers. These are not like the recent dating of the Bakshali manuscript. These are numbers. I can compute them to arbitrary accuracy. So if I get 3437, it means that he didn't have a good value of pi. So nobody could have had r equal to 3438 if this is the origin of 3438. So it's a cautionary tale for me that one should be very careful when one does the history of mathematics. The guesswork, yes, up to a point. But when things can be actually checked against numbers, one should be very careful. So pi is the sacred number. Okay, even if you don't know it, you didn't always know it very precisely, that's a universal constant. 3438 is not a universal constant. It depends on the value of pi. Now, the greatest advance Aryabhata's thinking brought to mathematics was the idea of working with differences and second differences. That there is no question about, so one has to know, where did that idea come from? If you read other people, especially those who came later, because there was not much writing on this kind of thing before Aryabhata, and you understand, especially if you read the work of the people of the Nila Valley, the Nila school, you see very quickly that the driving force is when things are not linear, when you have a function which is not linear, that is when you need to use things like calculus. Then the Indian way of doing things is linear functions they obey the rule of 3. The rule of 3 goes back to the Shilpa Sutra, similarity of triangles, right triangles, and so on and so forth. So if you have a linear function, then this functional differences being constant multiples of the interval is one way of saying the rule of 3, if you have a linear function. If the function is not linear, then delta fi is not constant. What you do is you take the next difference, second difference. If it doesn't work, you take the third difference. This is very well illustrated in later work, very, very clearly. Now, I want to say that this way of proceeding when you have functions which are not linear or curves which are not straight lines. Aryabhata has a very interesting example of two particles moving at uniform speed and meeting, and how the rule of 3 can be used in that context, but not if they're not linear. The motion is not linear. Then this principle, if you apply to the sine function, which is not linear, then what you get is the harmonic equation I wrote down earlier. Okay, as I said, it's most clearly stated in later texts. This is from Yukti Bhasha. This quotation is from Yukti Bhasha. And in fact, just before this, Jeshdeva says that the rule of 3 does not apply to arcs and chords. He says that. And he comes back and he says, do not apply the rule of 3 to the arc because the result will be gross. Now, Yukti Bhasha, it's a wonderful text because it's got several pedagogical tricks up its sleeves. It does many things which normally is considered bad in a textbook, but very good in a classroom, which is repeat important things several times till everybody is convinced that it is true. Okay. So this is, he clearly understood, thought that the deviation from the rule of three when you deal with arcs and chords is fundamental. So he said several places, and one place twice in the same passage. So the fundamental reason why this happens, according to him, is that a circle has curvature. So for me, this is the most insightful step in Aryabhata, in the entire book. It so happens that he needed it for the sine function, so he did it for the sine function. But the idea that you must now look at differences and try to control the nonlinearity by looking at successive differences is the grandmother, I don't say the mother, the grandmother of calculus, because that's how Leibniz begins his work on calculus. He says, see, Leibniz and Newton had a tremendous advantage. Descartes lived before them. So he made the discussion, the parallels between curves and equations, part of mainstream mathematics. So what you could do for a circle, what these guys did for a circle, people who came after Descartes could do for any curve, any conic section, for example. Okay, so that's Descartes draws these arbitrary curves. Newton calls them, mechanical curves and geometric curves, but any smooth curve was good enough for them, and that is thanks to Descartes. So for me, when you talk about the founders of calculus, along with Newton and Descartes, I'll put Newton and Leibniz, I'll put Descartes and perhaps also Fermat up to a point, because he actually applied the Cartesian methods to determine things we now consider to be exercises in calculus for the parabola and the hyperbola, conic sections. So the history of calculus is much more complicated than in the West, in Europe, more complicated than we normally learn. Now this, of course, I've already said that the roots of both these things go back to Shulba Sutra. The deviation, the rule of three and deviations from it goes back to similarity and scaling of right triangles in the earliest two books, Apastamba and Baudhayana. And the idea of using the half chord, I think, goes back even further. It comes with Baudhayana's first description of the determination of the east-west, north-south directions. And that itself probably goes back to the Indus Valley civilization, 2,000 years earlier, 1,500 years earlier. Well, this is Aryabhata as imagined by a modern man in Ayuka, Pune. Okay, I like this very much. I like this sculptural representation very much, because the 23-year-old young man, full of confidence, if not arrogance, it comes through very well. I mean, people say that, well, they probably the model, there is some classical Greek sculpture aesthetics in this. Well, that's not so bad, because he got the best idea from the Greeks, astronomically speaking. Now, the personal history. What do we know? We know very, very little. We know that he worked in a place called Kusumapura, which has never been properly identified. We don't know. It certainly is not Nalanda that we know, because Xuanzang talks about Kusumapura, and it's a long trip for him, 2-day itinerary from Nalanda to Kusumapura. So it cannot be. Some people say it is Patna, Patliputra. We don't really know. Okay, 23 years old, that is now part of the folklore. Everybody knows that he was 23. Then the other thing we know is the description is Ashmakiya by the first Bhaskara and Ashmaka Janapada Jata by Nilakantha. Now, Nilakantha has a habit of adding ja or jata to many such things. I personally think that he doesn't know that he was actually born in Ashmaka Janapada, but that he was of that of Ashmakiya extraction. That's what I think. Anyhow, it's very confusing because at that time there were two Ashmakas, and not quite at that time, a little before that. The first, which figures in many early texts, including I think Panini. I'm not very sure. Where coins belonging to them have been found. Many scholars have struggled with what Ashmaka was, where it was, and so on and so forth. And final result is that two of them identified. One is near Gandhara, the other is on the Godavari, around the place which is now called Python, Pratisthana. Which of them is the correct one for our Ashmakiya, our hero? We don't know. I would suggest, on the basis of other historical facts, that it refers to the Ashmaka near Gandhara. I'll see why in a minute. Wherever it was, what made him travel thousands of kilometers east, whether from Gandhara, whether from Python to Kusumapura? He doesn't say, nobody says, but historically we know certain things happened at that time. The 5th century was a very troubled period in North India, especially Northwest India. That was towards the beginning of the 5th century, the Hunas who came from Central Asia started raiding, attacking Northwest India on a massive scale, as bad as what happened later. And it is recorded by several people, including Chinese travelers, that they devastated the whole countryside. Especially virulent were the attacks on the Buddhist sites of learning, Buddhist monasteries, universities, and Takshashila was destroyed completely, turned to rubble and ashes in a very brief time. And the Gupta kings fought, especially Skandagupta, who defeated them somewhere east of Takshashila for the first time. They withdrew to Kashmir and they became Shaivas, and that's the origin of Kashmiri Shaivism. Subsequently, they attacked again, and they pretty much caused the downfall of the Gupta Empire. Now, along with this, one must ask, what happened to the people who were there? Thousands of people, many colleges, many monasteries in the entire Gandhara, from Swat all the way down to Islamabad, in terms of modern geography. There were many, many settlements. What happened to them? Of course, some people would have perished, but of course, there is never a total genocide. So many people were taken by the Guptas to the peripheries of their empire where they were safe. And this caused a very, very big change in the religious, cultural, artistic history of India, North India. This is extremely well established by art historians. There is no doubt about it. It's been very well studied. Several well-known people have worked on these questions. And in brief and very popular summary, this is the reason why Buddhism, which had disappeared from Eastern India, came back to Bihar and went as far east as Bangladesh. Sarnath, for example, the sculptures of Sarnath from the 6th century, they're all caused by this. Northwest India, Western India, Ajanta, Kaneri, Karla, all the sites, the famous sites, Buddhist sites in Maharashtra, for example, they all were revived at that time. Some of them had a strong earlier Buddhist history in terms of the Hinayana phase, but subsequently they disappeared. They were revived, but now in the Mahayana form, especially the Mahayana Buddhism of Gandhara, Yogacara, Ajanta, for example. You can see the two faces very clearly. Kaneri, which is not very far from Bombay, very close to Bombay, in fact, it's a wonderful sight because you can see everything in one place. I will summarize the art historical evidence for this very briefly. One of them is that the Mahayana Buddhism that came to these places is very much the Mahayana Buddhism of Gandhara, Yogacara Mahayana Buddhism. And one particular aspect of this is the transfiguration of the Buddha. Buddha became Amitabha, the infinitely radiant God, divine, absorbed into himself many, many iconographic details of Hindu iconography. For example, attendant female figures on both sides. there. And these scenes that you see here and here, the two panels, they're called the Ashtamahabhaya. These are scenes of the perils which travelers through difficult country faced. So this is the Thanksgiving altar. This is from Kaneri, Cave 90, the absolutely splendid sculpture. There are many such. Amitabha, there are many Amitabha figures, many Ashtamahabhayas. I've just shown this. I'm sorry for the quality of the picture, but this is scanned from a printed photograph. So there is no doubt that Buddhism revived. And the themes that you find are precisely the themes that you find in Gandhara. Suddenly they flourish in Eastern India and Western India, both places, away from Gandhara. So I personally think that Aryabhata was part of the migration. This is, theme which you meet over and over again in the history of Indian mathematics, how large bodies of people go from one place to the other, and as a result, bring new knowledge, revitalize existing stagnant cultures, and then mathematics in particular, Kerala, the same story. Yeah, this is the supporting evidence, and you can read it. I mean, Vasubandhu was a very, very great Mahayana Buddhist scholar, Yogacara scholar. He was in Takshashila, that is known. He has himself said so. Subsequently, others have noted, I think Chinese travelers have noted, that he was the first rector. Nalanda was founded 20 years after the destruction of Takshashila, about 460 AD. Dates can be off by maybe 5 or 10 years, not much. So, the question now is, there is no evidence that he was, absolutely none, no definite evidence at all. But that caused me to go back and look at some of the earlier readings of some of the verses, especially the benedictory verses in the Aryabhatiya. And if you read, most translators will say that the word Brahma occurs 4 times in the book. First verse of Gitika, last verse of Gitika, first verse of Ganita, last but one verse of Gola. All of them, the word Brahma occurs. So it's been said, I mean, if you look at the translations, you will find this particular Brahma written with a capital B and a long last syllable, Brahma. And that Brahma, as we know, is the Puranic God, the God of creation. On the other hand, it's masculine gender, being a male God. So you can check, Sanskrit is a wonderful language because I don't know anything about it. I know I can recognize meanings of words, but the grammar, the subtleties of grammar are beyond me. So I've consulted 2 great specialists. The one is my old collaborator, Bhagyashree, who's very, very good, and the head of the Department of Sanskrit at that time in Bombay University, Uma Vaidya. Subsequently, I've checked it with another young, fine scholar of Sanskrit in Calicut University, and everybody agrees. The first 3 occurrences of Brahma is in the neuter gender. There's no doubt about it. The last is consistent, the declensions. The last is consistent with both neuter and masculine. So, I read this as the masculine gender Brahman. This Brahman is the Puranic, not the Puranic one, but the Upanishadic one, whose roots go back to Rigveda book 10, the 123, I think, in which he talks about Ka, the God. Who? The God who. And what is the Aryabhata? The first statement, Gitika 1, Kam Satyam Devatam Param Brahma. So it is Ka, the Supreme God, who is the true Godhead, Devata, not Deva. So Aryabhata was very definitely not a conventional orthodox Hindu. He was, and I think it is not impossible that this is one of the reasons why Brahmagupta attacked him so violently. The other tenuous links with Buddhism, they're interesting, but they're not conclusive in any way. One is the the periodicity of the universe in infinite time, that's very much a Mahayana cosmogonic view. Amitabha, for example, presides so, it says so in the main text, presides over the infinitude of universes in space and time, and he has his bodhisattvas, Avalokiteshvara, Maitreya, who serve other functions. So that's a very, so which way it went, which way the influence went, I don't know. So Aryabhata's yuga is a very scientific notion. It's what? The least common multiple of all the planetary periods. That's what it is. So, my feeling is that this is it's a feedback into the Buddhist view of cosmology from the mathematical work that was going on during the Siddhanta times. The other one, which is fascinating actually, Aryabhata's description of the Meru mountain, the visual garden surrounding the Meru mountain, is an exact replica of the description of the Buddhist paradise called Sukhavati. That's also been very clear, very described in great detail by many texts, especially one called Sukhavati Vyuha. So there are these parallels. But on the other hand, it really doesn't matter, because by then Mahayana Buddhism was virtually indistinguishable from a certain form of Hindu things. I mean, I have myself seen, or many people have seen, 6th and 7th centuries Buddhist cave temples in Western India, Aurangabad, for example, in which the Buddha is accompanied not only by the goddesses, the female goddesses that we saw in the other picture, but by actually Durga and Ganesh. And there is no doubt that they are contemporaneous. They are not late editions. There is no doubt. So by the time, Shankara came and supposedly removed Buddhism from India, Buddhism had pretty much disappeared in spirit from India, become thoroughly Hinduized. Yeah. In the next, I will go a little faster. The Ganitha 11 has been very confusingly read by many people, because especially there is a reference to Chaturbhuja in it, which nobody seems to be able to make sense of. But of course, if you think of it as preparation for Ganitha 12, the statement of Aryabhata's rule, then the Chaturbhuja makes extremely good sense, because the sign difference formula in the geometry, there is actually a rectangle. And rectangle is the equality of the opposite sides of the rectangle is used in establishing a pair of triangles to be similar. So it makes very good sense as preparation, as the fundamental idea on which the sign difference formula is derived. Number one. So this is, and then of course there is this famous thing which also many people have problems interpreting it. Chindyat yatheshtani. The natural reading is, cut it up as you please, cut it up arbitrarily. Now, if you do that, then what does it do? This verse, what it does is, of course, it lays out the idea behind Aryabhata's rule. Then it also says you can make a sign difference table in arbitrarily small steps. And as we all know, Bhaskara 1 did not get the point. He actually thought pi by 96 was some sort of quantum of angle. You couldn't go below that, because if you did, then of course you can't put an iron ball on the floor, it will roll away. Famous passage. Bhaskara too definitely got the point, because in the Siddhanta Shiromani, in the Vasana, when he talks about the sign table, he actually says you can make it more accurate by cutting it into smaller bits. But that's it. He doesn't go beyond. Then of course the famous sphere formulae, the volume and the surface area of the sphere, what does he do? He actually uses the sign table to add up the sign differences. He could have just, he could have avoided all these things, and then he could have, and then of course the final formula he gives is the exact analytic result, 4/3 pi r cubed and 4 pi r squared. So clearly he knew what the answer should be, but there is no detail. There is no detail at all. There's nothing said about how he went from the approximate numerical value to the exact analytic form. So that's the reason why I say that he probably understood what was going on, but he wasn't very sure how to get there. So that vision that you must now make the pieces of the ark as tiny as you want to, was what Madhava realized. And in fact, he did better. Not only did he do it for rational multiples of angles, he did it for arbitrary angles. Any angle, he told you, you tell me the angle, I'll tell you the value of the sine in analytic form. And of course, very well known that this is not an easy thing to do. It's a very, this is the step towards calculus. It's a real step to calculus. The most important thing about the way it was done for me is that what you do is you take a finite geometric quantity, let's say the length of an arc. Then you want to make it as small as you want to make it, as small as you please, yateshtani. Then what you do is you divide it by a large number, which for Yukti Bhasha is parardham, which is 10 power 17. Then of course he subdivides those tiny bits into still smaller units. And then he says that at the end the parardham will go away from your formula because it will cancel in the numerator and the denominator. Effectively what it says is that make it as small as you want to by dividing by a number which is allowed to tend to infinity. So I call this procedure division by infinity. It's not a very good term. And those who know the kind of metaphysical agony that Newton went through to justify infinitesimal quantities, that is, things which are zero but not quite zero. Whereas what these guys did was to work with things which are infinite, not quite infinite. So no metaphysical complications. What D'Alembert called the metaphysics of calculus is completely transparent, clear, available to you, to anyone who can actually divide. And of course, the thing about Madhava's work is that you have to read Yukti Bhasha. There is no other text which describes it with the same insight, same care, same meticulous care, and the same attention to both the motivation and the details of the proof. Everything is proved, except two tiny little results, but they're not very important. Now, I want to say two things about the technical challenges that this work faced, and also to support the case that this actually is calculus. Yeah. This formula, those who have worked on these things will know this formula very well. This is used both in the derivation of the pi series and in the sine series. In the pi series, Fi is I power k, some positive integral power of I. In the sine series, it will be sine k theta divided by n, some fraction of the angle, its kth multiple, right? Now, this inequality is trivial to prove. It's not very difficult. It's quite straightforward. It was used in the discrete form in Europe in the 19th century by Abel. So it's often called the Abel summation formula or resummation formula. So when you look at the context in which it comes in Yukti Bhasha, for example, you wonder, what does this formula say? What is the root thing? And this is actually this identity. If I take the limit of n going to infinity and pieces Fi varying continuously with I, this is the same as this. This formula is the same as this. If I put everything in terms of integrals. Now, this formula is actually integration by parts. It is actually integration by parts. What you do is you call it, it's very easy to show this. So calculus was being developed under the surface, as it were, because we have a certain way of looking at things. We have our language, our modes of thinking, and we take them back to what they did. The first thing we have to do is to establish a bridge, a correspondence between what they're doing and what we think. And if you do it, many of the things in these things, which are in the beginning look like extremely clever tricks, they actually become part of an organic whole. And this is one of them. The other thing which I've always found fascinating is the integral of x power n, which comes in the tangent theta formula, the arctangent formula. That if you go through the steps in Yukti Bhasha, for example, and just pretend that you're not doing discrete sums, you're actually doing integrals. Then you say that how did they prove that the integral of x power n between appropriate limits is 1 over n plus 1? So you take those things and do it in modern differential integral calculus. It's an absolutely fabulous thing to do. It's very, very straightforward. You need induction. You prove it by induction, and you prove it by induction by using integration by parts. And that's an exercise, if there are students here, I recommend very strongly, because you learn many things by doing it. It's not very difficult. So the point of all this is to say that it is actually calculus that was being done. It was done only for trigonometric functions. And the reason for that is they were only interested in the geometry of the circle. In fact, if there is one universal theme in the story of Indian geometry, it really is the geometry of the circle. They never looked at anything else. So the epicyclic model was very popular in India for the very simple reason it works only with circles. There are no other curves in it, no closed curves, no other curves. So there is no doubt at all that this is what is done. Now, actually the best example of the calculus credentials of the work of Madhava, but this one is not explicitly attributed to Madhava by anyone. It is in Yukti Bhasha, which is the surface area of the sphere and the volume of the sphere. The derivation is given in complete detail. Go through it. There is no more any finite division. The division is from the beginning very tiny bits of the meridian circle. You don't see parartham in that derivation at all. It's clearly exactly as we do it in the classroom today. Infinitesimal slices of latitude integrate along the axis. That's how it is done. Sine series is very interesting actually from many points of view, because if you look at the combinatorial details of the formula, it works without replacing sine theta by theta. That is to say, sine theta by n by theta by n. It works. The combinatorials don't depend on the fact that sine theta by n is small. Theta by n is small. Whereas the arctangent series, the pi series, the fact that it is small must be included from the beginning, because the proof by induction doesn't work otherwise. It's actually asymptotic induction. It's not induction for finite values of the number n. It's for n tending to infinity. So the fact that nevertheless Yukti Bhasha replaces sine theta by theta from the beginning, and he says over and over again, I do this because I want a formula valid for sine theta as a function of theta, whatever theta is. Yeah, so why do people express reservations about whether this is calculus or not? This is calculus for trigonometric functions, not for general functions. One of them is that the fundamental theorem is not stated in generality. Fundamental theorem is used before the limit is taken, when it is actually a triviality. Okay? Then only calculus of trigonometric functions. Now, of course, Newton and Leibniz work with much greater class of functions, very, very large class of functions, but not the most general class of mathematical objects for which calculus works. For example, if somebody were to go and tell Newton and Leibniz that there is a thing called the Dirac delta function, or more generally, distributions, they would be very puzzled. They wouldn't know what they are. Certainly, you cannot draw a curve for a delta function. Cartesian methods don't work for them. Calculus works for them. You're not going to say, because of this, what Newton and Leibniz did is not calculus. It is. Okay. So limitations of the class of objects for which we're seeking a description in new conceptual language should not be considered to be a reason for rejecting it as new and original. For me, this is calculus. It is not pre-calculus. It's not proto-calculus. It is not something like calculus. It is calculus. The other thing was, the Taylor series, so-called interpolation series, is wrong. Shankaracharya wrote this, he wrote the first 4 or 5 terms in this. He wanted to iterate it. Now, it's very easy, if you go through the logic of how it is done, it's very easy to see that it's not calculus. It is what I call a samskaram series. That is, in Yukti Bhasha, in Kerala in general, there were many iterated refinings of mathematical results. and that is called samskaram. So it's one of the samskaram series. It is no validity as an analytic expression for the function sine theta. On the other hand, so it's what sometimes it is called the Taylor-like series. If you want the Taylor series, it's a triviality. You have the Madhava series. You also have the addition formula for the sine here. Somebody should really separate these buttons. Yeah, here. You expand sine cos delta and sine delta in power series in delta. What you get is the Taylor series for the sine. One step, one line. So it's not a big deal. Now, Shankara, who has written so many things, is a very clever man, tremendous versifier, extremely good with computations and calculations. But I don't think he understood Madhava. He understood Madhava as little as the first Bhaskara understood Aryabhata. Yeah. So why is it, for me, Madhava a great master? Because apart from the invention of calculus, he did many other wonderful things. I have a list here. It's really pure mathematics in the sense that astronomy is unimportant. I mean, nobody needs the pi series to infinite accuracy to do astronomy. Nobody does. Not required. Then the notion of a function as an assignment of a value to every point in its domain of definition. It's differential, it's integral, and then converting the differential equation for the sine into an integral equation for the sine and solving it by iteration. That's 19th century mathematics. Then this, the light not coming. No, it's not there. Anyhow, the quasi-piano approach to integers. There is a passage in the first chapter which is compulsory reading because he defines, he's very concerned with defining positive integers in a proper way because he's going to use them in inductive proofs later. So when he does that, so he says, so what is the next number? So he identifies, a number is defined by the numbers which come before it, the numbers which come after it, and he said the number after as a successor is the same as the result of adding 1 to the original number. Then he says, you take the step n times, that is the same as adding n to the original number. So it's an absolutely fascinating thing. Then of course, no, it really doesn't work. Yeah, there it is. Mathematical induction, infinite series as respectable mathematical objects for the first time. Now, I can't show you a picture of Madhava. Nobody has made a sculpture of Madhava. So what I show you is where he worked, where he lived, where he worked, and I will be finished in 3 minutes. Okay? 3 or 4 minutes. Yeah. So this is the basin of the river Nila. It is not called the Nila now. It's the classical name of the river. It is called Bharata now. The river is here. There. Let's come back. This is the road. This is the river. Okay. And this is the cradle of, from medieval times, the cradle of Kerala culture. And the villages where they lived are here on this arc. This is Alathiyur. Little above that is Trikandiyur, where Nilakantha was born. Little here is Thiruprangod, where Jeshadeva was born. And somewhere here, see this river joining here, this junction, is a place called Kodalur. I'll come to it in a minute. Remember this? This is where Kodalur is. This is the river as it is now, 10 years ago. It's a very beautiful river still, being destroyed. Great rate. It's a lovely place. What do we know? We know Madhavan was called Ilanjipalli Embran. Madhavan Ilanjipalli Embran. Now, Embran is a word which describes Brahmins from Tulunadu, from coastal Karnataka. They were all migrants. The big migrant story, another big migrant story. Migrations from north of India, primarily from an area just north of here, Vallabhi in North Gujarat, and from Ahichatra on the Ganga near Kanauj. And so these migrations have been taking place from about the 5th or the 6th century. And they settled in 2 sets of villages, 64 villages according to the legend, 32 in Karnataka, 32 in Kerala. And Alathiyur is one of them. Then this place called Shokapuram, where Chitrabhanu lived, is another. There are several others like this. Now, what we also know that his house, according to himself, is Bakuladhishtita Vihara. And that is in fact exact Sanskritization of Ilanyi Palli. You can match the colors. Bakula means Ilanyi, it's a flowering tree. And Palli is a Vihara. Palli is a very common name for villages and houses in South India, not just Kerala. He was Sangama Gramaja. And Sangama Grama, literal translation into Malayalam is Kodalur. Sangam is Kodal. There are hundreds of places in South India which are named after Kodal. Most famously, Kodala Sangameshwara of Basava. Kodal means a confluence. And of course, Ur is Grama. All right. So the natural thing to do is to identify Madhava with his Sangama Grama with Kodalur. It has never been done before. I don't know why. It's, it hits you in the eye. It's in fact, Kodalur is a rather famous village now because a very, very famous Malayalam writer and filmmaker actually is from Kodalur. Everybody knows Kodalur. Now, I will not go into the earlier controversies about where he came from. It's actually pointless. What is interesting is that there is a Kodalur Mana now. It's not in Kodalur village itself, some distance away. And the family has a wonderful story about why the home of this family is not actually in the village after which it is named. It's a very plausible story. I've been to the place. It's a very, very beautiful place. And what's remarkable is that the family memory goes back about 5-6 generations now. And they were extraordinarily distinguished people. They were not astronomers or mathematicians, but they were grammarians, they were linguists, they were people studying particularly all the Vedangas very closely. And what is most interesting is that the family is a very, very maverick family. I mean, the principal idol in the house, which is worshipped, is not of any of the Hindu gods and goddesses, but of Patanjali, the grammarian, the author of Mahapashya, is the main. There is a puja room. He's the main Pradhisthana. Very old sculpture. And I've no doubt at all that because there is Trivandrum Sanskrit College had a whole section, a fair collection of things, all of which marked Kodalur Manavaga. This is ex libris Kodalur Mana. It's printed, handwritten. So Madhava's things are understood. Now this you skip. This is because Madhava's case is particularly simple because everything fits. But many other people, like Alathiyur, for example, 3 or 4 different translations. They all used. Very confusing. So Kerala, of course, has an earlier history of astronomy. And that history is connected with Shankaranarayana and his teacher Govindaswamy and so on and so forth, 500 years before Madhava. So Madhava didn't come into virgin territory. It is not like that. There already was a tradition, and the 500-year gap is filled with names. We have no proof that they actually lived in Kerala, but K.V. Sharma, for example, believes they do. Perhaps he's right. And the 2 most prominent names are P.P Divakaran and Suryadeva Yajman. And they are followers of Bhaskara I. And the mathematics came, Aryabhatan mathematics came there as seen through the eyes of Bhaskara I. There was nothing else. But they were, many of them had turned into astrologers. Varaha Mihra was known. So the link to the past, that past is Parameshwara, because his grandfather, the student of a very, very famous astrologer, Talakkulam Govinda Bhattadiri, who was from Alathur village, and that tradition survives. The most expensive astrologers in this country today are in Alathur. That's the one visited by ex-chief ministers of Tamil Nadu, the presidents of Sri Lanka, everybody goes there. So it's very flourishing. So Madhava came from outside, brought with him new knowledge, new in mathematical perspectives. What was it that he brought? He brought Bhaskara too to Kerala. And I prefer to call this the Nila school, not the Kerala school, for this reason. And at least we're lucky, nobody has so far called it the Madrasi school of mathematics. So I'm not complaining too seriously. So there it is. And the point I want to make here is that Bhaskara's teachings came to Kerala through Madhava. There was nothing before that. And in fact, Lilavati, Parameshwara's commentary on Lilavati is probably the first of any of Bhaskara's works to be commented in India. Because Gangadhara's is about the same time, maybe 10 years later, according to François Pat. Let's see. And I think the link is Narayana, Pandita. And I've said some things there. You can look at it. You can ask me after the talk. I'm going to stop here. So there you are. Thanks very much.